Linear algebra. Sounds like algebra and lines together. And that is a lot of what we're going to be doing. Lots of applications, but a little bit of review of some of the linear systems of equation stuff you've done already. If you want to write a line in 2 dimensions, you could write it in general form or in y equals mx plus b form, where m is the slope and y is the y-intercept. And when you have a system of linear equations, you have more than one line, and sometimes those lines intersect, and that would be the solution to the system of linear equations. So what we're going to be doing in this unit is we're going to start off by reviewing how did we solve some of our equations in the past, 2 equations and 2 unknowns, and some of the strategies. What this unit does with matrices is it allows us and teaches us another method. And this other method will also be useful if you have 3 equations and 3 unknowns, or 4 equations and 4 unknowns. And it's a little bit more systematic, and it's quite easy to program computer science-wise, so it becomes a nice way to solve problems with computers. So here we are, 2 equations with 2 unknowns. There was 2 main techniques that you learnt when you solved these. Technique number 1 was called substitution. With substitution, you looked at your equations, and in this case we have 2, and said, is there a variable that's easy to get by itself? And in this case, looking at equation 1, oops, and second equation, does yours have an equal sign? Did I make it better on yours? It should be equals 1? Plus 1 equals 0. Okay, we'll keep it the same. We'll keep it black. There we go. That hardly noticed that there was a mistake in my notes, right? Okay. Substitution says, look at both equations. Is there an equation where it's easy to get something by itself? Yes, in the first equation, I can get x by itself easily. Then once you have x by itself, you substitute it into the other equation. So the other equation was 2x minus 3y plus 1 equals 0. But instead of x, I'm going to write 6 minus 4y in there instead. What that does is it makes a new equation with just one thing to solve. And if you just have one thing to solve, you can use your previous knowledge of equations and getting y by itself to completely solve it. So if I distribute my 2, I'm going to get 12 minus 8y minus 3y plus 1 equals 0. Negative 11y. If I move the 12 and the 1 over to the other side, is negative 13. And so y is 13 over 11. Once you have one of your values, you then can substitute that value back to find out what x is. Since we got x by itself and x is equal to 6 minus 4y, we can now say x would equal 6 minus 4, and instead of y, I can plug in the 11 over 13. 6 minus 2652 over 11. If I change that to 66 over 11, I would get x is equal to 14 over 11. A nice start with lots of fractions. So that was method 1 for solving a system of equations. I'm going to take method 1 and you make it smaller so it fits nicely over there, and split my page in half and say method 2. Method 2 that you could use to solve is something called elimination. In the elimination method, you tried to line up your equations so that things matched up perfectly, and then try to get one of your variables to have coefficients that are the same, except one is positive, one is negative. I like having one positive and one negative because then you can add the equations. Some people get them the same and then subtract, but I find students make more mistakes subtracting than when they add. So what I would do to equation number 1 here is I would multiply equation number 1 by negative 2. Equation number 1 would then become negative 2x minus 4y. I'd have a minus 12 on that side. I'll just keep it there. Equals minus 12. Why not? And then my other equation is still 2x minus 3y. And then if I move the 1 over, this needs to be 8, right? I needed to multiply that by 2. There we go. Equals negative 1. So I made a little mistake in that first equation. When you multiply by negative 2, you need to multiply the entire side by negative 2. So I need to distribute to hit the x and to hit the 4y. And if you do that, you can now add your equations. Negative 2 plus 2 is 0. Negative 8 plus negative 3 is negative 11y equals negative 13. And you would get y is 13 over 11 as well. And then you would do the same idea as plugging it back in to find x. Now, for a system of equations, we often write our solution as coordinates because there's an x value, which we figured out was 14 over 11, and a y value, which was 13 over 11. So we write our answer as the points where these two intersect. Why did I multiply by negative 2? I was looking at my x values and saying, what could I multiply one of the equations so that the coefficients, or the numbers in the front, were the same, but one was positive, one was negative? Because if they're like that, right, and I add, negative 2 plus 2 is 0. Sometimes you have to multiply both equations. Like if I wanted to make the y's the same, I have to multiply the first equation by 3, the second equation by 4, so that they both have a 12 in front. Okay? If you can just multiply one equation, it's nicer. It's easier. So when we solve that system of linear equations, we're looking for the point where they intersect. Now, a couple of other things for review. When you are solving a system of equations with two lines, there's 3 different things that could happen. You could have what's called an independent system, where the one line crosses the other line and you have one solution. This happens when you have just different slopes and doesn't need to necessarily, we can actually take this out. If you just have different slopes, you will always have one intersection point. It's impossible for 2 lines to have different slopes and never intersect. It's impossible for 2 lines to have different slopes and still be the same line. So all we need is different slopes, and we're going to get one solution. A dependent system is when the 2 equations are exactly the same line. Then there's an infinite amount of solutions. They will always cross. And so in this case, they would have the same slope and the same y-intercept because they would be exactly the same line. Or if you showed they had the same slope and one point in common, then they would have all their points in common. And finally, we have an incompatible system which has no solution. That would be 2 lines that are parallel. So now they have the same slope but a different y-intercept. these lines will never cross. So we've already talked about elimination and substitution. Another thing you could do is graph both the equations. And if you graph both the equations, you could find out where things intersect. The graphing, though, only works out nicely if the coordinates work out nicely when they intersect. The example that we did with 14 over 11 and 13 over 11, if you graph that, it'd be like, oh, they cross, but I can't tell exactly where. So the algebraic methods are better. Ooh, I like this one. Okay? If we start off with elimination, I could multiply the first equation by 2 to get my coefficients in front of x to match up. If I multiplied my first equation, everything by 2, I would get 2x minus 4y equals negative 2. And my second equation is still negative 2x plus 4y equals 2. And I add them up. 0 plus 0 equals 0. Okay? So what's x? What's y? What's the solution? What does this mean? Right? If this happened, would you feel like something went wrong? Feels like maybe something went wrong. This is going to tell us that we have a dependent solution. It wasn't really noticeable at the beginning, but those are exactly the same two lines. Whenever you get something that's always true, like 0 is equal to 0, always, okay? You have an infinite number of solutions. If we were like, I wonder if these are the same line, you could rearrange both of these lines into y equals mx plus b. The first one, can you see that I would have negative 2y equals negative x minus 1, dividing everything by negative 2 would give me 1/2 x plus 1/2. The second equation, 4y equals 2x plus 2. Divide everything by 4. 2 over 4 is 1/2. 2 over 4 is 1/2. We can see that those two lines are exactly the same. Oh, Alvin, just before you go. Now we want a system here so that there's no solution. No solution means the lines are parallel. So we need both of these lines to be parallel, but they need to have different y-intercepts. So what I could do with this is I could take both of these equations, the first equation here, and solve them, ky equals negative x plus 2, rearrange it into y equals mx plus b form. And the same thing with my second line. I could take it and rearrange it in y equals mx plus b form. If these lines are going to be parallel, they have to have the same slope. The slope of the blue one is negative 1 over k. the slope of the green one is negative k. What do we have then? We need that negative 1 over k, the slope of the blue one, has to equal negative k. And we take this equation and solve it. Multiplying both sides by a negative k would give me 1 is equal to k squared, which would tell me that k is equal to plus or minus 1. Oh, do you know what I really should have done in this question? I'll tell you afterwards. Both of those answers work. Okay? If we plug in 1 or negative 1, the slopes would be the same. And if we plug in 1 or negative 1, the y-intercepts would be different. The y-intercept of the green equation you can see is 4. The y-intercept of the blue equation is either 2 or negative 2, depending on which value of k. Now, what would have made this question really more intriguing? What would the best possible way would have been if here I had put negative 4. Because if k is positive 1, you would have had, here you would have negative 4 over k, right? If k is positive 1, I think I would like it to be positive 4. Yeah, even better. If I was a math teacher trying to find out if you knew every little detail, I'd make it positive 4. Why? Because sometimes you square root both sides and what do you forget? The plus or minus. Okay? I've never had a math student never forget that at least once. I know I've forgotten it probably more times than I could count. And then you would have to check, and only negative 1 would work. And positive 1 wouldn't work, because then they would be exact same line. But we don't have that. We have the easier question. And with that easier question, both plus or minus 1 would provide us with no solutions. Okay. So enough of the easy ones. Let's deal with some fractions. So I'd like you to try and solve for x and solve for y. You can decide if you want to use substitution or elimination, or whichever method you think would work the best. You're going to have to do some algebraic work to rearrange. The first thing that I did was I got rid of the fractions in that first equation. So I noticed if I multiplied everything by 6, I would get rid of the 2 and get rid of the 3. That would leave me with 3 times x minus 1, which would be 3x minus 3, and 2 times y plus 2, which would be 2y plus 4. And I rewrote that as 3x plus 2y equals 23, combining all my like terms. Then it seemed natural to use elimination because my y's were already matched up. So when I added them together, I got just 4x equals 28 and x equals 7. How many people use substitution because they could get the x by themselves right away? Okay, most of you, all of you. More than most. Okay. Was it more work or less work than this, or both the same? Both the same? You still had to get rid of the fractions in the other equation. And then you could plug it back in to solve for y. Okay, solving for y, it probably makes more sense to use this equation that's simpler rather than the more complicated one when plugging in x. And we always write our solution as a coordinate. So 7, 1. Perfect. Now, The next question has 3 equations with 3 things you don't know. Not sure if you've solved those before. If you haven't, you're going to try. This is a common technique using elimination. The idea is right now we have 3 equations, and I numbered them 1, 2, and 3, with 3 unknowns. If I take 2 of those equations, for example, equation 1 and equation 2, can you see it would be really easy to eliminate the x if I added those equations together? If I did that, I would get an equation that was y plus 3z equals 5. I'm going to call that equation A. If I choose 2 other equations other than equation 1 and 2, I could eliminate x again. So I decided to take equation 2 and 3. I multiplied equation 2 by 2 so that I could eliminate the x's again. And then I got y plus 5z equals 9. So you can always do this with a system of 3 equations. Choose one variable to eliminate first, and you will get 2 new equations with the 2 variables that are left. If you did this, you can now take equation A and equation B. I multiplied equation B by a negative so that my y's matched up, and I eliminated again. And I got negative 2z equals negative 4, so z is 2. Once you've got z is 2, you could plug that into either equation A or equation B and figure out what y is. And once you have z and y, you could plug both of those into equation 1, 2, or 3, and you could figure out what x is. And we write our solution as a coordinate with 3, x, y, and z, 1, negative 1, and 2. Now, this is a very typical method for solving a system of 3 equations where you choose one variable to eliminate first and then go from there. Okay? And in this situation, someone might say, Mr. JR, if you look at equation 2, it doesn't have a z already. Why not just use equation 1 and 3 and get rid of the z that way and use that new system? Perfect. That would work as well. Now I'm going to pull up some of your work because some of you used substitution and some of you used substitution and elimination and some of you used super elimination, which I'm going to call it, to see a couple of different and creative ways that we could do this. And that's the nice thing about these equations. This method that I have up here is a fairly common method for doing it, but I don't think it's the most elegant or easiest solution for this example. So here we go. I'm going to pull up a couple of examples. Let's start with yours. This first one has some substitution and some elimination. Can you see it, or is it too bright? It's too bright. Start it again. That's perfect. So in this one, it was really obvious from the second equation that we could get x by itself. Once x is by itself, we can substitute that into another equation. The careful thing that you have to do with substitution is you can't substitute it back into the same equation you got it from. Because if you do that, everything just goes away and you're like, what happened? So here, he took the x, which was 3y plus 4, and substituted it in to which equation? Into the top one? Okay, so 3y plus 4 minus 2y would be y plus 3z, and you move the 4 over to the other side right away. So he substituted it back into the first equation. And when he substituted it back into the first equation, did you also substitute it into the last equation? Okay. Substituted into the first equation and substituted into the last equation. And he got an equation, one that was y plus 3z equals 5, and another that was y plus 5z equals 9. Then he took the bottom one and subtracted the top one, so he started to use elimination. And because the coefficients of y were the same, you could subtract to cancel things out and got 2z is equal to 4. So then he got z is equal to 2. And from there, plug things back in to get -1 and 1 for x. Okay. Here is a super elimination technique. In this one, the decision was made to just add all three equations together. This doesn't always work, but in this example it worked beautifully. Because if I add all three of them together, my x's go away. My y's go away. Or wait a minute, do they? Oh, you multiplied one of the equations by -1. Oh, the top one. Okay. So first he multiplied the top equation by -1, and then when he added all three together, the x's went away, the y's went away, and you just got 2z equals 4, which allowed you to get z was equal to 2. Had to do a little bit of rearranging and stuff and substitution to figure out x and y, but once you had z equals 2, you just had two equations with two unknowns and could solve from there. So a mixture of substitution, elimination, adding together, all of those work. If we wanted, like what I provided here is a systematic way that we could go about doing this, where we choose to eliminate one variable first. But you could see in the systematic way it wasn't necessarily the fastest or the most efficient. But because it's systematic, it's clean, and you don't get lost in your algebra. Sometimes when some of these other methods, if you make one little mistake, everything goes bad really quickly. So we have to be careful. So here's your next problem. So the question is, how do kids without algebra figure this out? I saw some nice algebraic solutions. They're just smart. They just look and say, oh, I know that blue is usually the number 27, so I'm going to guess that. That's probably what they do. Just a fact. Yellow is 10, orange is 20, and red is 24. Therefore, blue must be 27. The logic is obvious. But what they would do is they would say, well, if I put these three scales together, what would happen? If I put this on top of here, I would have one cat, one dog, and two bunnies. And then if I took this scale and added it onto there too, then I would have two cats, two bunnies, and two dogs. So if I combined all three of those scales, I'd have two cats, two bunnies, two dogs, and it would add up to 54. So one dog, one cat, and one bunny would be half of that, 27. And then once you have this as 27, can you see how easy it is to find out how much the cat is? You just take away the 20, and the cat's 7. And once you've got the cat is 7, you could go, oh, the bunny is 3. Oh, the dog has to be 17. Okay? Systems of equations sometimes lends itself that way, that there is a nice method. Now, I'm not trying to tell you that you shouldn't learn the systematic way that I showed you and not have that in your toolbox to be able to solve things. But there are times where you can be creative, like in this one, and figure it out in a nice way.